to the analytical. Just I want to describe some more detailed analytical things, because already we said analytical method, it is going to be exact solution, but I'm going to ask some questions here. Okay, so first, the same problem I'm taking, we are interested to find out the stress. Okay, you know what is the stress, how to find out the stress. Okay, so load per area. Okay, so you get 20 Newton per millimeter square. So now, what is stress, my dear students? What is mean by stress, and what is stress? Stress is nothing but internal resistance done or offered by the material. Okay, it is very simple. Now I want to ask some questions. Okay, now you are applying the load. Okay, imagine you are not applying the load, just without load, stress will be there in a component or not? I want to know that. In universe, all the components are attracted by the gravitation force, so neglect that, leave it, it is common. Okay, apart from this, without considering the gravitation force, is there any other stress? Self weight. See, due to self weight only the gravitation force attracts, right? So self weight and gravitation force are related, same. Apart from that, is there any stress? You are not applying any force. So neglect the self weight, neglect the gravitation force. Apart from these two, is it any stress? When you apply an external load, I'm telling external load, the gravitation is, it is internal, it is available. Self weight is internal, it is available. So exclude those things. Apart from that, you are giving the external load of 5 kilonewton. Now I'm asking, I am not applying external load 5 kilonewton. So without applying any external force, is the stress is created inside the body or not? So if you apply external force to balance that external force, to hold that external force, so the material will give some reaction, that is called as a stress. It is very simple, my dear students. Now you are sitting on the chair, is right? That means what? You are sitting on the chair, that means your load is acting on the chair. Chair is very safe. That means what? The chair is a one kind of material that is offering, that means that is giving a resistive force, a reaction force to balance your weight, right? This is called a stress. So stress will be created when you apply a external force. Clear? Good. Now my second question. So you got 20 Newton per millimeter square. So now my second question is, where this 20 Newton per millimeter square will occur on the object. See now, you are applying the load at the end. The reaction will be happen here. So generally it will be, the stress will be maximum at the middle. We are assuming that the stress is uniform throughout the body. We are assuming, my dear students, please listen. We are assuming the stress is uniform throughout the body, but it is not exactly throughout the same. Okay, my next question is what? So now, can you imagine, once you apply the load, what will happen the cross section? The cross section may reduce, is right? Now, listen, there is an object, you are applying a external force, okay? After external force applied, the stress is created. According to the stress, to balance the stress, strain is created. The body is deforming. Okay. So after deformation, it will be like this, is right? See now, the cross section is changed. It will be like this. Clear? Now, stress 20 Newton per millimeter square. Where it will be? Tell me now. It will be at the ends, or it will be at the middle, or it will be constant and throughout the body. We studied this problem many times, but we didn't see those informations, right? Now, my question, you apply the load, the cross section is changed. So before that, the cross section may be something. So 250 mm square, right? Now, After applied the load, the cross section may be 100. Imagine the cross section may be 100 at this point. So what will be the stress? Stress is what? Load per area is, right? So load is what? How much? 5,000, right? 5,000 divided by 250 mm square become, see, before applying the load, it is 250 mm square. So you see the cross section, okay? After apply the load, the body is changed. So the cross section is reduced. So I'm thinking at this end. So imagine 250 become 100. So if you divide by 100, so what is the stress? 50 Newton per millimeter square. So 50 is right or 20 is right? Can you tell me now? Which is the right stress, 20 or 50? So at the end, the stress is 50. But by the calculations, we are getting only 20. We are assuming that the body is under Hooke's law. We are considering that the body is having uniform cross section after the application of load, before the application of load. This is the assumption we are taking. Whatever we are studying, this 20 is, that means what? That is a engineering stress, not a true stress. True stress is what? 50 is a true stress. Clear? So are you accepting this? So 20 is a engineering stress because we are made some assumption. Based on the assumption, we are calculating some values. That value is 20. So this may be a minimum stress or this may be an average stress by considering the initial cross section. My dear students, here we are considering the initial cross section. Why we are taking initial cross section? In the sense, we are assuming that the body is uniform throughout the process, before applying the load, after applying the load. But in actual, what is happening when you apply the load? So the body will extend, so the deformation will happen, the cross section is changing. So what is the real stress created? Then what is the maximum stress created? We need to study those things. Okay, so for that only we are going for FEA, finite element method. Okay, so we don't know at what cross section it will come here. We are assuming that it may be 100, but we don't know exactly. For 5 kilonewton, it may be 100. If it is 10 kilonewton or 8 kilonewton, what is the final cross section? We don't know. That is why we are assuming that uniform cross section. So whatever we are getting, whatever we studied, what are the data we are collected, so those informations are, those data are called engineering data, engineering stress, but that is not true stress. So true is something different, engineering is something different. So really something is happening, but we are studying something, right? Are you understand what I'm telling? So we are assuming something and we are studying some way, but really something is happening. So there is no connectivity. What we are studying in engineering, what is happening real, there is no bonding. There is no connection. Curriculum all over all the engineering colleges. So entire world is studying only the engineering data, engineering stress, engineering strain. That is why we decided to go Hooke's law. Here, so we are under some assumptions. Using those assumptions we are studying, but really happening something. So to find out what is happening really, we want to get, so we cannot get exactly what is going to happen really by 100%, but we can study, we can find out at least by 90%. For that we are developing finite element method, that is called approximation method. Okay, so this is what happening. So further we can develop to considering linear deformation, Poisson's ratio. So those informations we take, degrees of freedom, factor of safety. So those informations are coming to compensate those values. Okay, so 20 we are getting, right? But 50 may occur. So to compensate those values, we are considering the Poisson's ratio. we are considering the factor of safety. What is Poisson's ratio? Poisson's ratio is nothing but what? So see this component. So initial diameter is different, initial length is different. But after application of load, the length and diameters are changing perpendicularly, changing normally, right? So length is increasing, diameter is reducing. So two direction strain is happening. If you consider the two direction strain under the factor of safety, almost you will get the data as what we're expecting, right? Now coming to this one, this is what one dimensional problem. We are assuming that the object is uniform before and after the load. Okay, neglecting the self weight, neglecting the gravitation force. So we are studying the one dimension. That means what? If you study only the linear deformation, okay, without taking the Poisson's ratio, then it is said to be a one dimensional problem. We are assuming that the cross section changing only one direction, right? But in real, it is not happening. It is happening in two dimension. So if you extend the object, what will happen? See that diameter is increasing, so diameter is decreasing, length is increasing. So two directional strain is happening. Okay, considering the Poisson's ratio, we can go for two-dimensional analysis. Okay, so reducing means that is in x direction, increasing means that is in y direction. Considering those this Poisson's ratio, then we will get the maximum stress, maximum strain. Okay, that is also keeping assumption that it is under Hooke's law, right? These are the problem we are studying. Okay, so now coming to the discussion of true stress, engineering stress. So whatever we are studying in curriculum, that is called engineering stress, keeping some assumptions. But if you go for those assumptions we are studying, okay, so engineering stress is the stress calculated by taking the cross section of the object before it is loaded. That means what? Initial cross section we are aiming. Okay, true stress is what? Is the stress calculated by taking the current. That means after applying the load, what is the final cross section? If you know the final cross section, then we can find the exact stress what is happening. Okay, this is the difference between the engineering stress and the true stress. Okay, so this is what engineering stress we are calculating. Okay, right. Now we are going to find out the true stress. So how to find out the true stress? So for that, we are using the numerical method. Already we studied numerical method is a approximation method. Why we are going for approximation method? I want to find out, I want to study the exact behavior of the material, but that is not possible 100%. So that I'm going for trying to achieve 90% or 95%. For that, I'm implementing some concept, some methodology that is called finite element method. What does it mean by finite element method? Take the same example. See now, the body is same object, same load, but what I'm doing now, I'm dividing the part into number of pieces. Okay, so before that, what we are doing, so we are considering the entire length and entire object at a time. Okay, now what I'm doing, so I'm going to divide the component into number of pieces. Here it is divided into 4 pieces. So according to the load, what is the behavior of the first element E1? What is the behavior of second element E2? What is the behavior of third element E3? What is the behavior of fourth element? Then if I sum all this behavior, then I can go and arrive and tell the approximate 90% what is really happening. Is it clear? Okay, so this approach is called finite element method. Finite is what? So exact size, that is called finite. Okay, so dividing the object into finite size and study this. For example, let me take this one. So the same object I have drawn using the black diagram, by the black diagram. So this is the element divided at the first part. So E1, how it is behaving. So at the end E1, what is happening? At the end E2, what is happening? So this is called deformation U1, U2, U3, U4. Okay, similar way, what is happening at the end? What is happening at the end? So if I add all these deformations, then I can find the exactly 90 to 95% of the deformation I can find out. Clear? So what is the question here? Find the deflection of the bar. Here you can find the deflection 0.1. This is by considering the entire length, considering the entire object in a single time. But here what I'm doing now, the same deflection I'm going to find out, but the method is different. So I'm dividing the component into number of pieces. Okay, so what is the deformation at the element 1? What is the deformation at the element 2? What is the deformation at the element 3? Similar way, element 4. Add all these deformations, I can get the exact solutions. Okay, so I am now dividing into 4. If you divide into 8, you will get some more exact. If you divide into 10, you will get some more exact. That depends on how much divisions you are making. Okay, if you want to improve your percentage of accuracy, you can divide many number of pieces. Clear? Okay. How to find out, how to solve, and how to find out the behavior of this first element, and how to find out the first deformation of the first element. So there is a procedure called finite element method. Thus there is a matrix method we are going to follow. Okay, so that is also under the Hooke's law. Okay, so we are going to follow the elemental matrix. Okay, stiffness matrix, force matrix. There is some concept. So if you go for higher studies, you will come to know those things. Okay, considering the elemental matrix, stiffness matrix. So using Hooke's law, we can find out the deformation by using the boundary conditions. What is the boundary for element 1? Here reaction will come. Here there is no force. That is called reaction, zero force. And element 2, at the both ends, there is no reaction, there is no force, 0, 0. Element 3, so at the both ends, there is no force and there is no reaction, 0, 0. So at element 4, one end, there is no force, another end, we have a force, right? 5000. So considering these boundary conditions, applying these boundary conditions in the matrix, okay, so we can find out the deformation. So this is the way we can find out the, so this is the calculations. Okay, using the matrix method, we can find out the deformation. See the deformations here. See the deformations linearly, it is increasing here. 0, 0.025, 0.5, 0.7075, 0.1. See this. We found only at the end. What is the deformation at the different points? We are able to find by the finite element method. Okay, so this is the one. By using this deformation, I can go and find out the stress as well as strain. Okay, this is also an approximation method. Okay, right. Now the same procedure I'm going to follow. See this numerical method using a manual calculation. So what I'm doing now, just using the matrix method, I'm going to find out the deformations. The similar approach I'm going to do using Ansys program. Clear? If I use the same method of finite element using Ansys program, so what I will get, see now. Just I'm going to show only the minimum and results only. How to see how to do this Ansys data, I will teach you later, but I'm going to show only the answers. If you use the same problem to find out the deformations, the program, Ansys program, gives the total deformation is how much. So minimum is 0, maximum is 0.10003 mm. See this accuracy, right? So strain, see this. Stress, see this, minimum is this much, maximum 21.6. But see this calculation, we got only 20. See this deformation strain. See the deformations, maximum is 0.1. But see this result from the Ansys program. Stress is maximum 21. Okay, strain this much. Okay, deformations 0.10003. So this is what we are getting now. Clear? So by seeing this, what you can understand. So FEA, finite element, using the ANSYS program, we can get approximation solution nearer to the 100%, or I can say around 80, 95% to 98% exact solutions we are getting using ANSYS program. Okay, so now you can understand the importance of this ANSYS program, how accurate answers we are getting, right? So this program also works under the same method of FEA, but it is doing more calculations. We are dividing only 4 elements, but you can see here it is going to divide into number of elements. You can see here more than 5,000, 6,000 elements it will divide. So okay, so by manual calculations we can go for 4 divisions or 5 divisions, but using the ANSYS program you can go for any number of divisions. In terms of lakhs we can divide the component, we can study those things. So I will tell you that how to divide the component. Those things we will study later. Okay, right. Now